In this video, we are going to talk about objective lenses in the SEM column. So objective lens, it is the final lens in the SEM column, and also this is the this objective lens forms a fine probing form lens. So these objective lenses can be controlled by focusing, with the knobs during SIM operation. So this in this fine probe can be adjusted by controlling the current in the objective lens. Current in the objective lens to demagnify and focus the electron beam into the surface of the specimen. So sometimes these objective lenses may be overheat because of the high magnitude of the current passing through the objective lenses. So it needs some copper cooled some copper coolers also required to prevent overheating. So this objective lenses are three types mainly. Objective lenses are three types. They are first one, pinhole lens, immersion lens, and third one, snorkel lens. And this is also a combination of 1 and 2. It is combination of both pinhole and immersion lenses. Combination of 1 and 2 lenses. So now first we will talk about pinhole lens. Then after we will go to immersion lens, and then snorkel lens. These pinhole lenses, we can see this is the image of arrangement of the pinhole lens. Here in the pinhole lenses, the specimen is placed just below the optic axis and also it is just below the objective lens. So this is the specimen, and this is the objective lens, where here is the beam limiting aperture, which is here. This beam limiting aperture cut down the electron beam into the fine focusing electron beam, which focus onto the specimen surface. So whatever scattering electrons coming from the specimen, for example secondary electrons which are detected using ET detector. So here in pinhole lens, and the specimen is placed below the optic axis. So this pinhole lens, we also call it as out lens objective lens. because generally as this specimen is placed below the optic axis, so generally this type of pinhole lenses are used in conventional imaging purposes, used in conventional imaging purposes. So as it is placed below the optics, so there is a flexibility of keeping the specimen as large as possible. So there is no there is no restriction on the specimen sizes. So here no flexibility. Sorry, there is can be able to use wide range of specimens, wide range of specimen dimensions, and also wide range of specimen dimensions can be used up to usually up to specimens, and also we can be able to use wide at large working distances. Large working distance can be preferred. Large working distance can also be used. So whenever there are large working distance, that means higher depth of fields can be achieved. Higher depth of fields can be achieved. So here higher depth of here in the image, if we see in the image, these are the magnetic coils, and so the specimen is below the optic axis, so there won't be that much interaction of magnetic field. There is no interaction of magnetic field with the specimen So we can be able so here we can also be able to use magnetic specimens also. So that is also one of the advantage we can say. Here as we already said that large working distance can also be used here. So higher depth of fields can be achieved. At the same time, because of this we can also be seen large aberrations or defects. So there may be some reduction in reduction in resolution can also be seen because of lens aberrations. Because large aberrations are defects. Can affect high resolutions. Yes, because here the specimen is placed below the optic axis, so whatever electrons scattered from the specimen can be detected by using detector. As we in the ET detector, along with the secondary electrons, we can also be able to collect BSC detector. So there may be a degradation in resolution can also be seen when we use these pinhole lenses. So secondly, we will discuss about immersion lens. In the immersion lens, a specimen is placed within specimen placed within the specimen placed inside the bore of the objective lens. Bore of the objective lens. So here, as we need to keep the specimen inside the bore of the objective lens. So we need to move the specimen to raise its position. So here raise the specimen to the position of objective lens. As we need to raise the specimen, so there is a restriction in specimen. Restriction in specimen can be there. Restriction in specimen can be there. So usually this type of lenses can be used for nanomaterials. As here a very small operating at a small working distance, small working distance. So high resolution can be observed. High resolution imaging can be possible. So as the specimen placed inside, so we need to capture we need to detect the scatter detector. So for that TTL detector used to detect signals. TTL detector is used to detect the signals, and here highest image resolution can be possible. This type of lens can also be seen as called as in-lens objective lenses. So thoroughly we will talk about snorkel lens. Snorkel lens here, this is a combination of both pinhole and immersion lenses. Immersion lenses. Here specimen is placed. This specimen is placed immediately below the objective lens. Specimen placed immediately just below the objective lens, so that we can so that there will be both magnetic effects, and also the placement also the very close to the surface of the specimen. So here the relative placement of the sample such a way that both magnetic field of the lens extends to the surface of the specimen. This design, as we said, combines both pinhole and immersion type of lenses. It enables high resolution imaging while allowing for high resolution imaging, and also at the same time allowing for various dimension of specimens. There is no restriction, just not like immersion lenses. So here